Nuovo Pignone started designing and manufacturing centrifugal compressors in the early 1960s, quickly achieving a leading role and becoming internationally recognized in the area of centrifugal compressors. In order to more easily recognize the various types of Nuovo Pignone centrifugal compressors, it is important to understand the basic function of a centrifugal compressor. In a centrifugal compressor, a continuous flow of fluid increases its pressure by means of energy given by impellers arranged on a rotating shaft. This type of machine is composed of an outer casing, which contains the diaphragms and a rotor. The rotor draws gas from the suction nozzle through the impellers, across the diaphragms to the discharge nozzle located on the opposite end of the compressor. The major components of a centrifugal compressor can be divided into two functional areas. The first functional area includes the stationary components consisting of the casing, the inlet and discharge nozzles, the inlet and discharge volutes, the inlet, intermediate, and discharge diaphragm sections, the shaft end seals, the journal bearings, and the thrust bearing. The second functional area includes the rotating components consisting of the impellers, the shaft, the balance drum, the spacers, the seal sleeves, the thrust collar, and the locking rings. Gas flow enters the inlet volute of the compressor through the suction nozzle. The volute ensures uniform distribution of the gas around the eye of the impeller. In the volute, directly opposite the suction nozzle, is a fin that reduces gas turbulence and prevents recirculation within the volute itself. From the inlet volute, the gas is then drawn into the eye of the impeller and is discharged radially at a higher pressure, temperature, and velocity from the tip of the impeller. The impeller contains blades that convert the mechanical energy of the shaft into gas energy. This energy can be measured in terms of pressure, temperature, and velocity. The high-velocity gas flows from the impeller into the stationary components downstream, whose surface defines a diffuser. In the diffuser, part of the gas velocity is reduced. Following the diffuser is a return channel that brings the gas to the eye of the next impeller. Upon leaving the last diffuser, the gas flows into the discharge volute and is directed toward the discharge nozzle. The discharge volute contains a fin, similar to the fin in the inlet volute, that reduces gas turbulence and prevents the gas from continuing to flow around the volute. The increased energy in a gas is defined by the characteristics of pressure, temperature, and velocity. These three characteristics are used to determine a quantity known as enthalpy. Enthalpy depends only on the condition of the fluid and measurement of the energy content of the gas. Thermodynamic properties of the gas can be static or total. The difference between the two is that the total condition includes the energy content generated by gas velocity. Thermodynamics includes the concepts and laws describing the conversion of energy from one form to another, and the study of how these forms of energy interrelate. The assembly of the rotor begins with the installation of the sleeves to the area of the shaft where the oil seals will make contact. Next, the locking ring is threaded onto the shaft at the balance drum end. Then, the balance drum is installed and shrink-fitted on the shaft against the locking ring using double keys. Finally, the discharge impeller is installed and shrink-fitted on the shaft against the balance drum using double keys. Then the partial assembly is dynamically balanced. After the partially assembled rotor has been balanced, a spacer is installed, the next impeller is added, and both are heat shrink fitted to the shaft. Then the rotor assembly is balanced again. The sequence of balancing the rotor, installing the spacer, and adding the impellers is repeated until the suction impeller, spacer, and locking ring are installed and balanced as defined by the customer requirements. Generally, the thrust collar is added last. It is hydraulically expanded and pressed into position on the end of the shaft. The assembly of a BCL compressor begins with the insertion of the diaphragms into the counter casing. Because both the counter casing and diaphragms are horizontally split, each half of the counter casing receives the diaphragm halves. Each half is lowered into place and positioned axially by the counter casing shoulder. The diaphragms in the upper half of the counter casing are locked in place using cap screws so they do not fall out when the upper half of the counter casing is placed on. After the diaphragm halves have been mounted into the counter casing and placed in position, the labyrinth seals are installed in the diaphragm sections. The labyrinth seal segments for the impeller eye and foot are rolled into L grooves. The labyrinth seals in the upper half of the counter casing are locked in place using cap screws so they do not fall out when the upper half of the counter casing is placed on the lower half. The rotor assembly is inserted on the lower half diaphragms and rests on the lower half labyrinth seals. Then the axial position of the rotor is set and recorded. Next, the upper half of the counter casing is placed on top of the installed rotor and lower counter casing half. Before closing the counter casing halves together, O-ring segments, coated with lubricating grease, are fitted into position on the middle split plane of the lower diaphragm to minimize leakage between compression stages. Great care must be taken to ensure a perfect fit between the two halves to avoid internal damage to the rotor and diaphragm.